we could temporarily model as if it was right in the middle of that, so at 4 meters over. In addition, we have a 20 kilonewton load on the very end, and also, very strangely, on the very end, we have added a moment. We've added an applied moment on the end of it. And then when I look at these points, these reaction points here, this is a pin, so we can only provide an X and a Y. We cannot provide a moment resistance. This came up before lecture tonight, is just the fact that this pin is actually kind of useful when we're looking at the moment. Later on, we're going to look at this and say, well, you know what, we know something, that the moment is 0 here. At X equals 0, the moment is 0 as well, because it cannot provide a moment resistance at A, so it must be. B is even simpler. All it can do is push upward, because it can't even pull down. This pin at least can hold down, but this is just a one-direction support. It's basically a compression only. You can only push down on it. If we were going upward, it wouldn't do anything. So I know that load has to be this or it's 0. By has to be pointed up. AY, I'm guessing, is pointed up because we have a 320 kilonewton load coming down here, so pretty good guess. And then, really, this is trivial. When I look at that, I don't see any other horizontal loads, so I already know that is 0, that reaction AX will be 0. So when we look at that, we've got to go back to our earlier statics 1, and do summation of forces, summation of moments to solve for these reactions. I chose to take the summation of moments about A, so that way these forces which go right through A, just ignore them. So then I have this load, this reaction, that load, and indeed I actually have a moment here applied. It doesn't matter where it's applied, anywhere on that member, it provides a negative moment. All right, so I've got 320.
Okay.
Yes?
I'm just trying to visualize like the forces in my head with that moment out there on the end. Wouldn't that kind of be providing uplift at AY? Because of the pivot?
It would cause, yeah, I can see how it's
like
trying to bend
tunnel?
upward. It's trying to bend upward the beam. Basically, you're right, kind of, it's trying to bend the beam upward.
Isn't that why you count for it in the moments?
Well, later on, when we actually plot the moment, we would take anything that's causing an upward bend was negative moment. Anything that causes a downward bend is a positive moment. It's strange. That's what we decided to do. So I see what you're saying, but that 150 newtons, doesn't matter where it's applied, it is applying a moment to that member that is, because it's a moment, it could be applied anywhere on that member, and it is causing the same, well, I define it this way as positive, so it would be a negative moment by this definition right here. It doesn't matter where it's applied. I see what you're saying. You're saying, hey, this is causing this to uplift, so why wouldn't this arrow be downward? And then I would say, well, you know, you also have 320 kilonewtons pushing down here. I suspect that will override it. But you're right. This is providing a negative moment. Where and this, if you look at that 320 though, do you agree that 320 at 4 meters over is trying to spin it? If I define this as positive by right-hand rule, right now all we're doing is trying to solve for reactions. So we don't have to get into the shear and the moment analysis right now. We're just trying to solve for reactions. So we're doing basic statics right now. So if I take the moment about A and I define this right-hand rule as being positive, this is actually going in the opposite direction. It would be a negative. That's why I put a negative 320 times 4 meters. Actually, it should be 320 kilonewtons. And this B is actually trying to make it rotate in the same direction as I defined as positive right-hand wing. So that upward force, the AX, AY go right through it, so there's no moment arm. So you ignore those for this moment calc. And then I've got 20 newtons, kilonewtons going down, also causing a negative. This is being applied in such a fashion that it's trying to, if we were in outer space, that 150 kilonewton meters would try to get the whole thing to spin, right? And it wouldn't matter where you apply it, it's trying to get the whole thing to spin with 150 kilonewton meters of applied torque to it. In this case, that arrow is going the opposite direction of what I defined as positive. This is trying to cause a negative moment around AX at least. I have only one unknown, the By. I brought that over to the other side. Clearly it was a negative at first, but then I took everything else and multiplied it out, and I got a negative, dropped the negatives from both sides. Divide both sides by 8 meters, and I got 206 kilonewtons. If this is pushing upward 206 kilonewtons, and I've got 20 kilonewtons down, 320 kilonewtons down, this has to push up the remainder. In the case I'm doing a summation of forces, the moment has no effect. So when I do the summation of forces in a y direction, a moment has no effect, nor does any forces in the x direction. So if I do summation of forces in the y direction, it's only loads that are in the y direction. I know I've got some unknown pushing up, I'm pretty sure of that. 320 down, 206 up, 20 down. So when I add all those numbers up, I get a negative number, bring AY to the other side, it's negative, drop the negatives from both sides, and you'd have 133.75 kilonewtons. This has to be 133.75 up if this is going to be 206 up. So you are right, it did lessen it some, because this is only 133 of that 320. Instead of being half of that, which would be 160, it's only 133. So it did lessen it. But it wasn't enough to overcome it. If this load did not exist, it would be interesting to see what would happen. We wouldn't even hold it down. The pin would have to hold down. All we have done, because this is step one, all we have done is figured out the external reactions. And one of the things that was thrown us the other day was this distributed load was temporarily modeled as a single point load in order for us to do this, just the calcs for the reactions. Now, that's it. We're done with that. To solve for reactions, we're using basic statics. Now we're moving on to try to shear diagram and moment diagram. And when I look at this, one of the things I brought up with a couple students before class is what we learned the other day about method of sections, where if we have a beam, say this is point A, and this is point B, this is point C, if we wanted to, we could do a bunch of method of sections at key points. Say, okay, what's the shear here? What's the moment there? What's the shear here? What's the moment there? If you did that, if you took a bunch of methods of sections, you could actually plot those, and you would have a shear and a moment diagram. So that, always remember, you can go back to fundamentals and just find out, okay, what's the shear in the moment right here? Do your calcs, do the, what we were doing the other day, the method of sections. I know it would be a pain because you'd have to do a billion of them, right? But if you had to, if you were like, this doesn't seem right, and I want to check myself, you know what, I'm going to just do a method of sections right here, because I should get the exact same number for my shear and my moment at this point as I see in my diagram, my shear and my moment diagram. So that's, bringing it back to fundamentals. The shear and the moment should be the same whether you're using these graphing techniques or you're stepping back and doing method of sections at these individual points. So when I look at this, I say, well, shear-wise, I'm pushing up, 133.75 right there. And then I have this uniformly distributed load that's pushing down 40 kilonewtons every meter. So we're going downward. And then we push upward again, 206. And then we come back down 20 kilonewtons back to 0. That's just shear, just looking at it from a shear perspective. So let's just see if we can model that shear. Can we sketch up that shear? So that was one of the big things, is understanding that this is a distributed load, but it's a uniformly distributed load, and it's 40 kilonewtons per meter. So, and notice how it's pointed down. So that means it should be a minus 40. We're going downward, minus 40 is what our slope should be. We're going downward by a slope of minus 40. So when I sketched it, I said, well, load equation, and it's only valid from 0 to 8. Yeah, that's right, because this distributed load only goes for the first 8. So when I say the y is equal to 40, it actually should be y is equal to minus 40. Oh, but I said here negative, pushing down. Okay, should have put, well, down here I recovered. I put a negative sign. So my y, this is before I do my first integral. My y is equal to negative 40 from 0 to 8. And what that means is I just have a load, distributed load that's minus 40 kilonewtons, minus 40 kilonewtons per meter. So in order to find my shear equation, I'm going to go ahead and, actually, it's interesting that I integrated that and I got my equation of my, and then the second interval would get you your moment equation, that's right. So, and again, this is only valid from 0 to 8. After that, we're outside of our uniform distributed load. If I integrate a minus 40, it goes up 1, our exponent would be x to the 0, which we normally don't write, but it goes up 1 to x to the first power. And then whatever your power is, you put it in the denominator out front. Well, minus 40 over 1 is still minus 40, so you don't write a 1 there. Plus a b. The b is the unknown. It's something that we have to solve if we know a given point. We happen to know that the shear at point A, which has an x distance of 0, at x distance of 0, the shear is 133.75 right there. So that's the number I plugged in to solve for the constant, the b constant. I plugged in 133.75 at an x equals 0. By doing that, then I found my b, and then I could rewrite my equation. Y is equal to minus 40x plus 133.75. And that totally makes sense, because I should be able to plot points, right? To be able to sketch this out, I should be able to plot points. At 0, if you put a 0 in for x, I have 133.75. We know that. We also know that it's positive, right? That's also it's also called the y-intercept, right? So there was another way that you could have actually sketched this up from the equation of a line. All right, so y is equal to minus 40x. So if I go forward 1 meter, well, I'll put 1 meter in there, subtract 40 from 133, I'm already 93. So I go over 1 meter, I'm already down to 93. If I go over, say, 3 meters, well, I'll be minus 120, so I'm at 13. So looks like every 2 boxes, so I want 2 boxes per meter. So by the time we get, here's at 3 meters over, we're getting close. Once we get to 4 meters over, we're already into negative territory. 4 times minus 40 gets me minus 160. Yep, I'm into negative territory already. So we just keep going down at minus 40 every meter. We keep going downward until we get all the way to 8 meters. And at 8 meters, we're down at 186, minus 186. Why? Because we went downward 320, right? But it's distributed, and we go only minus 40 every 1 meter. Then we have a...
Can I ask?
Yeah. Oh, yeah, totally.
I think you might have just answered it for me,
Yep,
but
yep.
At position 8 on the x-axis,
Yeah,
I
8
wanted
meters
that.
over.
Yeah, I wanted that to be the 206. Like just my head wanted it to be that because that was at point, at the by.
It is 206 that you are pushing upward, but if you go down 320 from 133, you're only at minus 186.
Right, that's why I think you just answered it, because I think you said that, but that's,
Well, it's because you're going from,
That
the
line
overall
going
force
up.
is 320 kilonewtons of force, because you're looking at the distributed load. That's the difference from 133 to the negative 186.
Oh, it's 320 down.
Right,
yeah.
that's the change.
But if you go up 206, you're at a positive 20, so you know you're gonna be coming back down 20.
That's what it is.
And there's the down 20.
This line is the 206,
Yeah.
okay.
So if we go up 206, we're a positive 20, so you know at some point we gotta come back down to minus 20, and that's what,
How come
that's
we
what
didn't
that
have to
last load
split
is.
that? Because I was looking at some of the examples and it took this just simple load and it split it, half of it was negative and half of it was positive.
Oh,
I know I missed
see what you're
last
saying.
week, I'm sorry.
And the reason why is,
Sorry if
what
everybody already knows.
no, it's okay. No, it's what Ben brought up. Ben brought up the fact that we have this weird thing that we're adding 150 kilonewtons of torque on the end, and so this 320 is not, the load is not equally supported by AY and BY because you have this unusual torque beam applied on the end, so it's not gonna be this nice half and half thing, which a lot of the problems were. A lot of the problems were half and half because you would, we have this distributed load, half of it goes here, half of it's supported here, half of it's supported here. That's not the case because we're adding, out at the end, we're adding this weird torque that's trying to bend it up. So this side here is only having to push upward 133, whereas this one is pushing up 206. So that distributed load right there is not, it's not as simple because of this unusual moment being applied on the end, trying to lift that end, if you will.
So we had to have that 20 kilonewtons to compensate for that 150 in the torque?
Well, no, that's what, that 150 does not, you don't see it directly in the shear values. You can't say, I've got 150 shear at that. But it definitely has an effect when you're doing your counts, when you're taking a moment about A, for example. You're gonna see that it changes your reaction loads. Your reaction loads are affected by it, and then those reaction loads will show up in your shear. So you don't see directly 150 kilonewton per meter moment showing up in your shear. You don't see it directly, but indirectly you do see it because your reactions have changed because of it. It's like an indirect approach, but it is in there. It has an effect. And when we move forward with moment, you will see it in that. You will see basically a spike load, a moment spike load. Right at that point, you're applying 150 kilonewtons. And because it's actually causing the beam to try to bend upward, it would be a minus 150 kilonewton meters. When we have established this equation for this line right here, the y is equal to minus 40x plus 133.75, we can take the second derivative, another derivative of it, to find the moment. This is the equation of the shear from 0 to 8. To find the equation of the moment, we take the second derivative of it. We basically go upward one more time. So that's what you see on the bottom of the page right here. I said I took that equation of the shear, and then I took the second derivative, well, another derivative, not derivative, another integral of it, sorry. We integrated a second time. Gonna have trouble tonight, I think. All right, so this time though, we're going from x to the first power up to x to the second power. And that too, whatever is in the exponent comes out in front in the denominator. And then same thing here, we go from 133.75 x to the 0 power, which we don't normally bother to write, up to x to the first power. Well, that has no effect in the denominator, but that did that too. So 40 divided by 2 is 20. I needed to solve for my c, my constant. And that was another question that came up before class, is how do I know the moment is 0? at x equals 0. So at x equals 0, right here, how do I know the moment is 0? The only way to know that is that this is a pin. A pin reaction right here cannot provide any moment resistance. When you look at how we sketched up the supporting reactions, we did not show a moment at all on that because a pin cannot provide a moment resistance. In fact, if the member was free to move, it would just rotate around that pin. The whole thing would go flop, flop around that pin, but it would spin around it, right? It doesn't have a moment resistance. So I know that at x equals 0, that the moment, or the y value, the moment is 0. So in order to find my constant, I plugged in, for x equals 0, I plugged in a y is equal to 0. So when that happens, you're going to find, if I put in a 0 and a 0 and a 0, all I have is c is equal to 0. So basically c is not, the constant is 0, so it's not an effect. Here is our moment equation right here. And that moment equation is only valid from 0 to 8 meters. Because that's where we have our distributed load. It's only valid along that distance. So my only option now is to plot points because I just can't see that in my head. So I took that equation, the minus 20x squared plus 133.75, from 0 to 8, and I started plotting points. 0, 0, obvious. 1, 2, actually there's 4, there's 6, and then 8 is already down here way low, minus 120. So that makes sense because you have the positive side of this has a head start, but this is squared, so it very quickly catches up. 8 times 8 is 64, but 4 times 4 is only 16, so very quickly it starts catching up. That's why the negative side will win. You see how it just keeps going down, it passes it by. So at x equals 8, all the way over at the very end, we're at a moment negative 120. So we learned that a positive moment is trying to bend upward, and the negative moment is causing a downward bend, right? No, other way around, sorry. Positive, negative. When I say it right but didn't do it right with my hands, when I try to curl the beam upward, it's negative. There we go. I'm trying to push it down, that's positive, because that's normally how a beam is loaded, right? So that would be, a positive is when the beam is basically trying to bend downward. Okay, now let's see, does that make sense with our initial sketch? We have a massive load here being applied early. And at this very end right here, there's really, you know what, the only thing that's causing moment is that 20 kilonewton load and this 150 kilonewton load. Both of them would actually cause this to try to bend upward, wouldn't it? And that's going to cause that to try to bend downward. That's 20 times 3, that's only 60 kilonewton meters around B, whereas this would be 150. So this 150 right here is enough negative so it's causing it to try to bend upward. I think that 150 is going to rule early, and I think that's what's going to happen. So let's see, let's sketch the end. So what happens at the end? All right, so we're definitely at minus 120. And then there's my 60, my positive 60 that I returned. I said that this guy here was trying to push down, causing at least this portion of this beam to try to deflect down. Yep, and when you deflect down, that is positive. So that's why 20 times 3 is positive 60. So that's why I had a return here of 60. And then at the very end, we're reaching out and we're basically putting a torque wrench on at the very end. And we're applying a torque. It would try to get that beam to bend upward. So that's why, you know what? With that, actually, it would try to get it to bend upward back here, but at this point on the end, it's just like that 20 kilonewtons. It's trying to bend downward on that end. It's hard for me to see because it's cantilever. It's not supported out there. So I think that should be positive, which would make sense because then it would return it to 0. that was, there's some tough stuff in there, that's not just like easy. Not easy at all. Huh. The next one is not really a moment, sheer moment. You have to figure out the maximum. So you have to figure out the total load being applied. We learned that in the case of a triangle, it's 1/3 of the way from the base, so you can model this as a single point load, figure out what your shear is gonna be. Largest W allowed if the shear max is 800. So you can solve for that W that would cause a shear max of 800 and a moment max of 1200. It looks to me that the moment max governs over the shear max. That moment max of 1,200 foot-pounds happens roughly 4 times earlier than the shear max of 800 pounds. That one's not too bad. But this one, let's just take a quick gander at it, get you on the right. So I had to solve for those loads. I'm confident you can do that with, and solve for those loads. During this portion right here, we have a distributed load, but at least it's uniformly distributed, it's not a triangular load. So I would expect to see a -4 slope, right? A -4 slope. So when I, at least between